China's moon rocket versus NASA's SLS. American engineers are shocked by the difference, and once you see it, you can't unsee it. You're looking at two machines built to reach the same moon, but designed with completely different beliefs about the future. NASA's SLS produces about 8.8 million pounds of thrust at liftoff, more power than 160 Boeing 747s. Combined, you heard that right. And yet, raw power isn't what's causing the real shock inside engineering circles. Because the biggest gap between these rockets isn't size, it's strategy. Now you step closer, and the real question begins. What are these rockets actually built to do? Mission drives everything. You're looking at two rockets that seem to chase the same destination, but the moment you dig deeper, you realize they're not chasing the same outcome. On one side, you have NASA's Space Launch System, built to carry you back to the moon under the Artemis program. It's bold, it's powerful, and it's designed to remind the world that the United States still leads in deep space exploration. When you step into this vision, you're not just visiting the moon, you're proving something. You're planting a flag again, building a presence that connects to something bigger, something historic. And beyond that, there's Mars. That's always been the unspoken promise behind SLS. But then you turn to China's Long March 10 and the feeling shifts. Because here, you're not stepping into a moment. You're stepping into a system. China's lunar strategy doesn't revolve around a single defining mission. It unfolds in phases carefully planned, tightly controlled, and quietly executed. You're not just landing on the moon. You're building towards something that stays. Robotic missions lead into human missions. Human missions lead into infrastructure. And infrastructure leads into permanence. At first glance, it feels less dramatic, less cinematic. But this is where the tension begins. Because while NASA is designing missions, China is designing continuity. And that difference changes everything. When you look at Artemis, you see complexity, multiple partners, international cooperation, commercial contracts, and layered systems working together. Orion spacecraft, lunar gateway, human landing systems. It's a network of moving parts, each one critical, each one dependent on the other. When it works, it's powerful. But when one piece slips, everything feels it. And that's where the unease starts to creep in. Because China's approach strips much of that away. Long March 10 is being developed as part of a tightly integrated national program. Fewer moving parts, fewer external dependencies. You're looking at a system where the rocket, the spacecraft, and the mission architecture are all aligned under a single direction. It's not just engineering, it's coordination. And for many engineers watching this unfold, that simplicity is unsettling. Because simpler systems don't just move faster, they fail less often. But this was just the beginning. When you zoom out, the contrast becomes sharper. NASA is building for flexibility missions that can evolve, expand, adapt over time. It's a system designed to grow outward, to open doors for partners and future technologies. China, on the other hand, is building for execution, clear milestones, defined timelines, minimal deviation. And now you're caught between two philosophies that don't just compete, they contradict each other. Do you build a system that can do everything, even if it takes longer and costs more? Or do you build a system that does exactly what you need and nothing more? Because once you ask that question, you start seeing the rockets differently. SLS begins to look like a symbol of ambition, massive, capable, but burdened by everything it's trying to carry. Long March 10 begins to look like a tool focused, efficient, built for repetition. And that's when the real tension hits. Because in a race to the moon, the winner might not be the one who gets there first. It might be the one who can keep going back, again and again, without slowing down. And suddenly, you're not just comparing missions anymore, you're comparing momentum. Because the moment one system proves it can sustain a presence launch after launch, mission after mission, the entire balance shifts. And it wasn't just about reaching the moon anymore, it was about who could stay. Now, you're ready to look closer, because once you understand the mission, the next shock comes from how these rockets are actually built. Inside the rocket design now, You move past the mission and into the machines themselves, because this is where the differences stop being philosophical and start becoming physical. You're staring at NASA's Space Launch System, and the first thing that hits you is scale. This rocket is not subtle. It stands over 320 feet tall, built around a massive core stage, powered by 4 RS-25 engines, the same engines once used on the space shuttle. These engines are not new. They are upgraded, refined, and pushed harder than ever before. And when they ignite alongside 2 solid rocket boosters, the result is raw, overwhelming force. 8.8 million pounds of thrust at liftoff. It's not elegant. It's not efficient. It's power delivered in the most direct way possible. But then you look closer, and something feels off. Because this rocket isn't just built, it's assembled from legacy. The engines come from a previous era. The boosters are evolved from older designs. Even the manufacturing approach reflects decades of institutional knowledge layered on top of itself. Every component has history behind it. Every decision carries weight. And that's where the tension starts to build. Because while heritage can mean reliability, it can also mean limitation. Then you turn to China's Long March 10, and everything changes. The design feels different immediately, cleaner, more deliberate. Instead of relying on older systems, this rocket is being built from the ground up with modern architecture. You're looking at a modular core stage, paired with liquid-fueled boosters, all powered by a new generation of engines. Instead of solid boosters, which burn fast and cannot be controlled once ignited, China is using liquid propulsion systems that offer more precision, more flexibility, and more control. And that changes how the entire rocket behaves. Because now, you're not just launching, you're managing the launch. But this was just the beginning. As you compare the two sides by side, the philosophies start to clash in ways that are impossible to ignore. SLS is designed to do one thing incredibly well: lift extremely heavy payloads in a single, powerful launch. It's built for maximum capacity, capable of sending over 95 tons toward the moon in its later configurations. When it launches, it carries everything with it: crew, cargo, mission hardware stacked together in one massive push beyond Earth. It's brute force engineering. But Long March 10 takes a different path. Instead of relying on one massive launch, it's designed around multiple launches working together. Components can be sent separately, assembled in orbit, and then pushed toward the moon as a unified system. It's not about doing everything at once, it's about doing it in sequence. And that's where things get uncomfortable. Because while SLS impresses you with what it can do in a single moment, Long March 10 starts to impress you with what it can do repeatedly. And suddenly, power alone doesn't feel like the deciding factor anymore. Then came the most surprising realization of all. The more complex a rocket becomes, the harder it is to scale. SLS, with its massive structure and intricate supply chain, isn't designed for rapid production. Each unit is a major undertaking. Each launch represents years of work, billions of dollars, and countless moving parts that all have to align perfectly. But Long March 10, it's being designed with repetition in mind. Modular components, streamlined manufacturing, a system that can be reproduced more efficiently over time. And that difference starts to echo louder than the engines themselves. Because in the long run, the rocket that launches more often learns faster. And the rocket that learns faster evolves faster. And it wasn't just about engineering anymore. It was about adaptability. Now you're no longer asking which rocket is stronger. You're asking which one can keep improving without breaking under its own weight. Because the moment you see that shift, the next question becomes impossible to ignore. How much does all of this actually cost? The cost of power now. You're stepping into the part of the comparison that's making engineers stop mid-sentence, because this is where the numbers stop being impressive and start becoming uncomfortable. You already know SLS is powerful, but power comes at a price. Each launch of NASA's Space Launch System is estimated to cost over $4 billion. That's not a rough guess. That's the reality of building, assembling, and launching one of the most complex rockets ever created. Every component is specialized. Every stage involves contractors, logistics, testing, and integration at a scale that few systems in history have ever attempted. And when you hear that number, it almost doesn't register at first. $4 billion for a single launch. Then it hits you. That's more than the annual GDP of some small countries. You heard that right. And suddenly, the rocket doesn't just feel powerful. It feels heavy, because every launch carries not just payload, but expectation. And that's where the tension begins to tighten. Because when something costs that much, you can't afford to fail. You can't afford to move fast. You can't afford to experiment. Every decision becomes cautious. Every change becomes slow. Every launch becomes an event that has to justify its own existence. But this was just the beginning of the problem, because it's not just about how much a single launch costs. It's about how often you can launch. SLS is not designed for high cadence. You're looking at best, 1 launch per year, maybe 2 under optimal conditions. That means every mission has to carry enormous weight, both literally and strategically. There's no room for iteration, no room for rapid learning cycles. And that's when the pressure starts to build. Because space exploration isn't just about reaching a destination anymore. It's about sustaining access. Then you turn to China's Long March 10, and once again, the contrast sharpens. While exact figures are less transparent, everything about its design points toward lower cost per launch, simpler manufacturing, more centralized control, fewer external contractors, a system built to reduce friction at every stage of production, and more importantly, a system built to launch more often. Because when your costs go down, your opportunities go up. You can test more, adjust faster, improve continuously. And that creates a completely different kind of momentum. But here's where the tension reaches its peak. Because lower cost doesn't automatically mean better capability, and higher cost doesn't guarantee success. So now you're caught in a dilemma that engineers are still debating. Do you invest in one massive, near-perfect launch, hoping everything works exactly as planned? Or do you build a system that allows for multiple attempts, knowing that progress comes from repetition? Because once you see it that way, the real difference becomes impossible to ignore. SLS is designed to minimize risk per mission. Long March 10 is designed to absorb risk over time. And those are not the same strategy. Not even close. Then came the most unsettling thought of all. If one system can launch 5 times for the cost of one, which one learns faster? Which one adapts? Which one quietly pulls ahead while the other is still preparing for its next attempt? And it wasn't just about money anymore. It was about tempo. Because in a race like this, speed isn't just how fast you go, it's how often you move. Now you're starting to see the real divide, and it leads directly into the next battle. Because cost and cadence are only part of the speed equation. The real fight is happening at the heart of the engineering itself. Reusable or expendable. Reusability changes everything now. You're stepping into the most divisive question in modern rocket engineering, and once you see it, you realize this is where the philosophies truly split apart. Because every rocket comes down to a simple choice. Do you build it to fly once, or do you build it to come back? NASA's Space Launch System makes that choice very clear. It doesn't come back. Every time SLS launches, you're watching billions of dollars burn, separate, and fall away forever. The core stage is discarded. The boosters are gone. The engines, some of the most advanced ever built, are lost after a single flight. It's a system designed for maximum reliability in a single moment, with no expectation of recovery. And at first, that makes sense. Because when your mission carries astronauts beyond Earth orbit, failure is not an option. You don't take unnecessary risks. You don't experiment mid-flight. You rely on what you know works, even if it costs more, even if it's less efficient. But this was just the beginning of the trade-off. Because every time you throw away a rocket, you reset the entire process. You rebuild, you reassemble, you respend. And that creates a ceiling, a hard limit on how fast you can move forward. Then you look at China's Long March 10. And the answer isn't as simple, but that's exactly what makes it interesting. At its core, Long March 10 is also largely expendable, but it's not designed in isolation. It's designed as part of a larger roadmap, one that is already moving toward partial and eventual reusability across China's broader launch systems. You're seeing early decisions that make future upgrades possible, engine layouts that can evolve, structures that can adapt. It's not fully reusable today, but it's not locked into being expendable forever. And that difference changes how you think about it. Because now, you're not just looking at what the rocket is, you're looking at what it's becoming. Then came the most uncomfortable realization. Reusability isn't just a feature, it's a philosophy. When you build for reuse, you're accepting that your first version won't be perfect. You're designing for iteration, for learning, for failure that leads to improvement. But when you build something expendable at this scale, you're aiming to get it right before it ever leaves the ground. And that creates pressure, because perfection slows you down. Iteration speeds you up. And suddenly, the gap between these two approaches starts to widen. Because while SLS is focused on delivering flawless missions, systems built around reusability are focused on getting better with every flight. And it wasn't just China thinking this way. Across the global space industry, reusability is becoming the standard. Rockets that land, boosters that fly again, systems that reduce cost not by being cheaper to build, but by being used more than once. And that makes SLS feel different. Not obsolete, but out of sync with where things are heading. But the silence didn't last, because defenders of SLS will tell you something important, and they're not wrong. Reusability adds complexity. Landing rockets is hard. Refurbishing them is hard. Ensuring they are safe to fly again is even harder. Every reused component carries history, and with that history comes uncertainty. SLS avoids all of that. Every launch uses brand new hardware. No wear and tear, no unknowns from previous flights. It's clean, controlled, and predictable. And when human lives are involved, that matters. But here's where the tension peaks, because safety and sustainability are starting to collide. You can build the safest rocket in the world, but if you can only afford to launch it once a year, are you really building a long-term presence in space? Or are you staging occasional visits? And that question doesn't have an easy answer. Because now you're balancing two different kinds of risk. The risk of failure versus the risk of falling behind. Then came the shift that changes everything. If one system can reuse, iterate, and evolve faster, even if it starts imperfect, it may eventually surpass a system that was designed to be perfect from the start. Not immediately, but over time. And space exploration is a long game. So now, you're not just asking whether a rocket comes back. You're asking whether a program can adapt. Because in the end, reusability isn't just about saving money. It's about unlocking speed. And once speed enters the equation, the entire race changes. Now you're ready to zoom out, because rockets don't win this race alone. The real battle is happening in everything built around them. The real race unfolds. You pull back, expecting clarity. But instead, the picture gets bigger and far more unsettling. Because these rockets were never the full story. They're just the front edge of something much larger. You started by comparing thrust, payloads, and engineering choices. You measured power against efficiency, cost against capability. But now you're seeing what those rockets are actually feeding into. And suddenly, the comparison changes completely. NASA's Space Launch System doesn't stand alone. It feeds into Orion, a spacecraft built to carry you safely beyond Earth orbit. It connects to the Lunar Gateway, a station that will circle the moon like a permanent checkpoint. And surrounding all of that is an entire network of commercial partners, private companies, building landers, cargo systems, and future infrastructure. At first, it feels like strength, because you're not looking at a single program. You're looking at a coalition, a system designed to bring in innovation from everywhere. Different companies solving different problems. Different nations contributing pieces to a shared goal. It's ambitious, it's flexible, it's open. But then the tension begins to rise. Because the more pieces you add, the harder it becomes to move them all at once. Every mission depends on multiple systems being ready at the same time. The rocket, the capsule, the lander, the station, the logistics, the coordination, and if one of them slips, everything waits. But this was just the beginning of the problem, because space doesn't reward complexity, it punishes it. And the more interconnected your system becomes, the more fragile your timeline starts to feel. Then you turn to China's approach, and the contrast hits immediately. There's no sprawling network here, no web of competing contractors. What you see instead is control. Long March 10 isn't just a rocket, it's a piece of a tightly integrated system where the spacecraft, the lander, and the mission architecture are all being developed together under one direction. You're not waiting for external partners to deliver critical components. You're building everything as one machine. And that changes how progress feels. Because instead of coordination, you get momentum. Instead of negotiation, you get execution. And for many engineers watching this unfold, that's where the real concern begins. Because integrated systems don't just move faster, they compound progress with every mission. Then came the shift that turns this from a race into a strategy. Because landing on the moon is no longer the goal. Staying there is. NASA's vision talks about sustainability, long-term presence, a future where humans return again and again, building capabilities over time. But the structure itself is rotational. Missions come and go. Hardware cycles in and out. The system evolves, but it doesn't anchor itself in one place immediately. It grows outward, but slowly. And that creates a subtle tension, because a system that is always evolving is never fully established. Then you look at China's trajectory, and the intent feels sharper. This isn't about repeated visits. It's about building something that doesn't leave. Robotic missions, preparing landing zones, infrastructure tested before humans arrive, plans for a lunar research station that isn't temporary but expandable. You're not cycling missions anymore. You're laying foundations. And that's when the realization starts to sink in. Because the first system to achieve continuity on the moon doesn't just participate in exploration, it defines it. But the silence didn't last, because NASA's model has a strength that isn't obvious at first glance: freedom. A system where companies can compete, innovate, and push boundaries independently, where breakthroughs can come from unexpected places, where one advancement can ripple across the entire architecture. It's unpredictable, but that unpredictability can create leaps instead of steps. And now the tension becomes impossible to ignore, because you're no longer comparing rockets. You're comparing two ways of building the future. One is structured, centralized, and designed to move forward without deviation. The other is open, distributed, and designed to evolve through collaboration. And both have consequences. Then came the most uncomfortable realization of all. The rockets you started with? They don't decide the winner. They only decide how the system begins. Because once infrastructure exists on the moon power grids, habitats, communication relays, it starts to shape everything that follows. It determines where missions land, how they operate, how easily others can join, or whether they can join at all. And suddenly, access becomes something else entirely. It becomes control. Then came the moment where everything clicks into place. Because SLS, for all its power, is tied to a system that moves carefully, deliberately, and at a pace defined by coordination. Long March 10, for all its efficiency, is tied to a system that aims to build, expand, and solidify presence as quickly as possible. And that's why engineers are paying attention. Not because one rocket is bigger, not because one is cheaper, but because one system might reach the point where it no longer has to compete. Because the moment operations on the moon become routine, the moment launches stop being rare events and start becoming supply runs, the moment infrastructure stops being assembled and starts being used, the race changes. And at that point, it's no longer about who gets there next. It's about who everyone else has to work around. And that's the part no one says out loud. Because it's not just about exploration anymore. It's about presence that turns into permanence. Permanence that turns into influence. And influence that quietly redraws the map of space itself. So now, when you think back to the beginning, when this felt like a simple comparison between two rockets, it almost seems incomplete, because the real difference was never just in thrust, or cost, or design. It was in what those rockets were building toward. And one of those visions doesn't just aim to reach the moon, it aims to make sure it never has to leave.